Yes, let me take this question over here.
Well, it seems to me you went at great length based on the various cosmological models to establish that you can't escape that there must have been a beginning. But the cosmological models will never provide a satisfactory basis for that proof because they cannot be observed. Wouldn't it be much easier to establish that fact on the basis of the second law of thermodynamics, which we do observe, which would require a beginning of the universe?
I disagree with the notion that because something isn't observed, that therefore we can't make retrodictions just as we can make predictions. That would destroy not only cosmology, that would destroy paleontology, geology, any of the historical sciences. So I think we shouldn't fall into this trap of thinking that you have to be able to observe things in order for these to be scientifically respectable theories. There's very solid evidence for the Big Bang. I mentioned 3 points: the galactic redshift, the nucleosynthesis of the light elements, and the cosmic microwave background radiation. Now, in my written work,
that's highly debatable, sir.
Well, I think I detect now where you're coming from based on some of the things you said. But I think those provide good evidence for cosmic beginning. But let me say that in my written work, like the book, The Kalam Cosmological Argument was mentioned, I have a second scientific argument for the beginning of the universe based upon the second law of thermodynamics. And what I try to do there is to show that given the second law of thermodynamics, a universe which exists infinitely into the future will come to equilibrium, will come to heat death. And therefore, if you have a universe which has existed from infinity past, it should now exist in a state of equilibrium or heat death. And the fact that we don't shows that the universe must have been created a finite time ago and simply had its low entropy condition put in as an initial condition at the beginning of the universe. So I think that your argument based on thermodynamics is a very sound one, and in many ways an even better argument than this one because, as you say, thermodynamics is so well understood, whereas this universe prior to the Planck time is not understood. So the thermodynamical argument is a very, very good reason also, a second scientific confirmation for premise 4.
The time zero just switches back the other way before the Planck time.
My comment is...
Yeah, I don't think that works, Victor, as I explained in our debate that we had.
Well, yeah, if you had the universe...
Well, now we should let this...
No, but it has to do with this.
Well, yeah, but we do want to respect the questioner here who's asked a question. Let's let him finish his point.
Well, I think the preference for that argument is that it is a scientific argument as opposed to a metaphysical argument, which is where I would put all of the cosmological theories.
All right, again, I don't want to repeat myself, but I don't think this is metaphysics that we're doing here tonight. I do offer metaphysical arguments, but I think this is good empirical science. But on that, we just disagree. Yes, way in the back here.
I disagree with your premise number 4 for the following reason. I think that if you're making any extrapolation beyond the Planck time, earlier in time, basically physics breaks down. So you don't have any model for quantum gravity, which means we have no viable candidate for saying that there is a singularity or that there's anything else. In fact, all of these models that you're positing are actually just working through the various implications of quantum gravity. So first of all, I think that that's a problem. I also think that the Hartle-Hawking model is a particularly intriguing one, simply for the fact that it uses a very basic fact about the Minkowski metric of space-time, that the signs of each space and time are opposite. And so that if you actually try to find what the metric measurement is, you will end up with an imaginary time at that particular moment, given the conditions that Hawking and Arnold posit. So I would like to know why, for example, you say that it's so clear that there's a singularity that has to exist, because I don't think that there's a very good physical argument that can be made for that.
Yeah, I think it's important to understand that the argument tonight doesn't depend upon the existence of the singularity. As I say, you can have perhaps a model like Hartle and Hawking's, which begins to exist. The universe comes into being on these kind of models, but it doesn't do so at a singular point. So nothing hangs on the singularity except that that is predicted in the standard model based on general relativity, and it makes the beginning of the universe very evident.
General relativity breaks down for Planck time. So
Right. And so the hope is that we'll be able to find a model that will enable us to describe physically that regime, and that's the holy grail of physics. It's going to involve an integration of quantum theory and relativity theory, and we hope that that will be found, of course. But whether that will serve to, I think, restore an eternal universe is very dubious. Charles Misner, cosmologist, once described it this way to me. He said, "It is as though a tiny window shade were drawn over the first split second of the existence of the universe, and we can't describe what happens behind the shade." But he says, we know that it doesn't come back out on the other side. And all of the attempts to try to make it come back out on the other side continue to fail. So while this isn't ever an open and shut case, it's always going to be a probability argument and always revisable in light of future discoveries. I don't think there's any denying that the best evidence that we have does support premise 4 rather than it's contradictory, and that therefore we ought to go with that. Now, with respect to the Hartle-Hawking model, what they do is not at all natural, I don't think, because it's true in special relativity.
It's used all the time in special relativity.
Well, I was going to comment on that before you interrupted. In special relativity, you have a pseudo-Euclidean space-time, and you can turn that, which means that it has a slight curvature, but you can turn that into a flat Euclidean space-time by substituting in imaginary values for the time coordinate. But all physicists recognize this as simply a mathematical trick. It's just a way of converting a pseudo-Euclidean geometry into a Euclidean geometry by using imaginary values for the time coordinate.
It's a physical mathematical trick, just as multiplying by some exponent raised to ikx will turn you into a wave function. It's a physical argument.
It's not a real description. You can't turn space-time itself from one sort of geometry into another just by changing the sign of the time coordinate. I mean, this is something you do on paper. It's an empirical matter whether or not time has a pseudo-Euclidean or Euclidean geometry, and you can't decide that question just by changing the sign of the variable in your equations.
There's no observation that is made at that point.
What?
Or there's no observation that can be made to say what happens. We have no theory that works at that point, nor do we have observation. So to make a theory that works in that regime, it's perfectly reasonable to take something that is a perfectly reasonable physical mathematical trick, if you will, and apply it to that.
So long as you understand that it is a mathematical trick, just as I said. And way back in 1920, Sir Arthur Eddington speculated on the substitution of imaginary numbers for real numbers in special relativity. And he said, this is just a mathematical device which has no ontological significance to it. It's just a different way of describing the same geometry. It's just a different description. Now, as Vic was saying, in quantum mechanics, when you do calculations with these complex numbers, you convert back to real numbers at the end to get some physically significant result. In Hawking's model, he just declines to convert back to real numbers. He keeps it in the imaginary regime. If you convert back to real numbers, presto, the singularity really appears. It reappears. It was really there all the time, but it's just concealed behind this mathematical trick of imaginary time. Yes?
First, I just want to thank you for coming out.
Sure.
Really appreciate it, and I'm reassured that the Christian mind is a powerful mind going through that.
Thanks.
In your book, Time and Eternity,
yes,
you write that, and I'm going to just change this up.
All right.
That some readers of yours have been surprised when you express, or when you remark that someone designed the book more about God's attributes of omniscience would be better advice for reading the works of Christian philosophers than of Christian theologians. Do you still think that's the case?
Okay.
And